final frontier. This is Sci-Fi Overdrive on Business.
Oh, okay, you need to stop doing that.
Okay, this is Sci-Fi Overdrive on Business Talk Radio, and we are going into the final frontier. Eric.
Captain, we'll be speaking with Dr. Michelle Fowler of the Space Infrared Telescope Facility. On main screen, now.
I cannot take it much longer!
Okay, I guess I gotta throw in somebody from Voyager, so we've got all the tracks covered at once.
Oh, that'll be cool. Yuji
Wake up and say something! Wake up and say something!
Anyway, we actually do have very interesting guests as we discuss real science on Sci-Fi Overdrive on Business Talk Radio.
The old, the cold, and the dirty this hour on Sci-Fi Overdrive.
Visit our website, www.scifioverdrive.com.
On this broadcast of Sci-Fi Overdrive, we're exploring both the universe and the Enderverse. Joining us now by telephone is Dr. Michelle Fowler. Dr. Fowler manages the SSC Education and Public Outreach Program. She also writes a monthly science column for the Christian Science Monitor and has made numerous appearances on television, although this will be her first appearance on Sci-Fi Overdrive. She received a bachelor degree from Harvard in 1992, a PhD in astrophysics from Georgia State University in 1998, and when she's not being absolutely brilliant, you can see her Renaissance dancing, singing, and acting. Thank you so much for joining us on this broadcast of Sci-Fi Overdrive.
Hey, great to be here. Thanks.
And congratulations on the successful launch last week of the Space Infrared Telescope Facility.
Oh, yes. Well, that's a load off my mind, obviously.
Yeah, especially considering, well, let's go in the Wayback Machine here. This thing was originally scheduled for launch much earlier this year, yes?
Yes, it was. Well, there have been a number of delays throughout the years. I remember when I signed on to the project, it was going to launch in December of 2001. So, and that was just 5 years ago. So there have been a number of different stages to the development of this launch. but it's finally off.
Now, were some of them weather-related? Were some of them, unfortunately, disaster-related? I mean, just what were some of the reasons that the project was delayed?
Well, there are a lot of reasons for delays. For any of the long delays, it more has to do with how ready people feel to launch, how the funding situation is going. Most recently, we had a delay from April, and that was due to some more development that was needed on the spacecraft, some more things that needed to be checked out. This week we had a delay because there's a tracking ship that was supposed to get into place over in the Indian Ocean. It was actually going to track the rocket as it went up and into orbit. And there was a huge storm off the Cape of Good Hope off of Africa. And so they had a lot of trouble. They were in 30-foot seas, so we couldn't actually launch until that ship got more stable and in the right position.
Yeah.
Yeah, so it's all kinds of stuff all over the world can really...
That's right. I have no idea. Yeah, the Indian Ocean storm held us up for a few days.
Yeah.
and I guess this is really odd because the Space Infrared Telescope Facility, once it goes out there, this is not going to be like its bigger brother, the Hubble Space Telescope. It isn't as if the space shuttle can just fly up to it and boost it into a different orbit or do something like that, right?
That's right. This is actually a trailing Earth orbit, and what effectively that means is we ping it all the way off the Earth. We actually give it escape velocity, and it falls into its own orbit around the Sun. We call that a heliocentric orbit. And the reason we see Earth trailing is that it kind of lags behind the Earth in its sort of same orbit around the Sun. And over time, the Earth will eventually catch up with it. I think in about 60 years, Earth will actually probably smack into the Earth. So it's a different orbit. It's actually the first time we've tried an orbit just like this.
Well, because, one of the staples of science fiction is the alternate Earth, the Earth that's opposite the Sun, but also 93 million miles away. Or 150 million kilometers.
I hadn't heard that one, but I'll take your word for it.
Well, yeah, it's sort of a Star Trek. At least I know that it's in the Gore novels, too. So this is the first time we've ever tried to put a satellite in the same orbit that Earth is, but it'll fall. Why are we doing this? Why not have it like the Hubble Space Telescope?
Well, this is an infrared telescope, and we commonly think of infrared as being heat radiation. So in order to actually detect the heat from the stars or from very distant galaxies, your telescope needs to be very cold. And the operating temperature of the inside of this telescope is 5 degrees Kelvin. So that's 5 degrees above absolute zero.
Wow.
Very, very cold. And any environment right around the Earth or the Moon is just too warm. There's too much infrared radiation coming from the Earth-Moon system. So we knew right away that we had to get this thing pretty far away from Earth. And this seemed to be a pretty good budget option. I mean, one place you could go is like L1, actually put it at one of the Lagrange points. But this was a little bit more cost-effective, a little bit cheaper, and it gets us far away from the heat of the Earth.
Now, is it going to be difficult to keep in contact with this kind of satellite if, as you said, it's going to be lagging behind the Earth and the Earth is eventually going to swing around and catch up with it?
Actually, it turns out that was one of the major advantages of the orbit, that the spacecraft is much easier to communicate with. Usually you have to worry about getting in the way of the Earth or in the way of the Moon as you orbit around, and there are sort of communication blackout periods. In this case, we'll know where Surf is in the sky, and we'll be able to communicate with it much more directly. There won't be any periods of blackout from the Earth or the Moon.
Interesting. I guess one of the questions is, the Hubble Space Telescope orbits around the Earth once every 90 minutes, so there are like 45 minutes when it can be used, and then 45 minutes when it's in the sunlight, so to speak. So, Space Infrared Telescope Facility can do nonstop observations.
It can, and I'm not actually sure. I think with the Hubble, as long as the Hubble is looking away from the Sun and the Earth, then it can still operate during part of its orbit. I'm not sure that it can't operate during the entire day cycle. But yeah, that's actually another advantage. There are areas of the sky that Surf will be able to look at continuously. It actually will sort of cycle around the sky in the course of a year as it orbits the Sun, and we'll actually be able to see much better coverage than traditional telescopes get.
So it's cost effective, you get better communication, and you can actually look at the sky longer. So why is this
it's
the
all
first?
Good.
Yeah. Well, so why is this really one of the first times that satellites are going to be placed in this kind of orbit?
Well, I suppose the thing is that it is non-serviceable. The astronauts cannot go up and bring new instruments, or in our case, the big deal is to fill our liquid helium dewar. The telescope is kept very cold by liquid helium, and the liquid helium will run out over a period of probably somewhere between 2.5 to 5 years. We're not really sure exactly yet. And when that's done, then that's pretty much the end of the mission. With some of the instruments, we'll still be able to operate to some degree, but the sensitivity just won't be as good. So that's a bit of a bummer, that this is a great observatory. It's one of NASA's big space telescopes, but we have a much reduced lifetime.
Yeah, I called Hubble Space Telescope its bigger brother because it's one of the 4 great observatories.
That's right.
Hubble Space Telescope, Chandra X-ray Observatory, which, as its name implies, looks at the X-ray part of the spectrum, Space Infrared Telescope Facility, and last but not least, there's the Compton Gamma Ray Observatory, right?
Yep, those are the 4.
Now, but there was a predecessor before SIRTIF went up, and that would be IRAS, the Infrared Astronomy Satellite.
That's right, exactly. Yeah, that went up in the mid-'80s.
And that was kept cool by liquid helium too, right?
Yes.
And I seem to recall one thing that really surprised the scientists was that in a weightless environment, the liquid helium didn't get used up like you guys thought it would.
Everything is model dependent, and one of the really amazing things about this mission is that we don't really know how long we have. The models all suggest we have around 2.5 to 5 years. Some of them suggest even longer, maybe up to 7 years. But once we actually get that puppy gone into space, we don't really know how it's going to act, how it's going to behave. And right now, literally, there are people glued to their computer screens watching the thermal curve of this as it cools off in space. We really just weren't sure how it was going to work. The cooling seems to be going very well. It's actually cooling down a little faster than we thought it would, which is great. And we just don't know how this stuff is going to act once it's up in orbit.
Well, how warm is it right now? I mean, when you launched from Florida, it must have been like, what, 350 Kelvin?
Oh, yeah, parts of it were room temperature, obviously. And I'm not exactly sure if the entire cryo array has been turned on yet. There are a lot of things that are going to happen in the next couple of days. And at one point, they'll open the valves and get everything flowing through the liquid helium system. I'm not absolutely sure that that's occurred. I could check the schedule. So there's lots of steps before we're really out of the woods. We have many different checkouts to do in the next few weeks.
So we're going to get this. We got the satellite up here. It's going to be operational. What's going to be the first thing you guys are going to be looking for?
Well, that's classified. I'd tell you, but I'd have to kill you.
Okay. Never mind. We'll just bleep it all out.
Oh, right. No. Well, I can tell you a little bit about some of the things that we'll be observing very soon. We've actually decided what the early release observations, a great acronym, ERO, yet another TLA, 3-letter acronym. And So we have all of the first observations decided on, mapped out, timed, scheduled, all of that. We're going to be looking at some of the warm protoplanetary disks. They're actually disks of dust around stars that planets form out of. We'll be looking at some very distant galaxies. There'll be probably some beautiful images of star-forming nebulae regions. So those are all things that I know will be some of the very first observation sort of takes. As far as what the very first release will be, that's up to NASA headquarters to release.
There's also another great, if she told us she'd have to kill us sort of thing behind it, which is that obviously Space Infrared Telescope Facility is a bit of a loser acronym.
Sort of, yeah, not a very good acronym, actually.
And there was a contest that was held for students, K through 12, right?
It was actually open to any member of the public.
Oh, okay.
So it wasn't actually limited just to students, but we got a lot of suggestions from students.
And it was to name this brand new telescope.
That's right.
And they have chosen the name.
Yes, they have.
And they're not telling us it.
That's right.
So some kid somewhere is going, they chose my name and I can't tell anybody.
That's right, I know. Yep, we've got them signed to a confidentiality agreement and all that.
Oh, so when do we find out that?
Well, I think that's going to be released along with our first observations in December. And I know everybody groans and says that's such a long way off, but the infrared telescope has been unusual in that it'll take several months to really get into true operating mode. It'll take us a while to cool off, a while to get everything calibrated and ready to go, and it'll also take a while to actually reduce the data and get it into a publicly presentable form. Mm-hmm. So with all of that, we're actually trying to look at mid-December now for the data release, the first beautiful images, and probably the name with that.
Okay, we're going to take a brief commercial break. When we come back, Dr. Thaler is going to tell us why she digs things that are old, cold, and dirty, and we're going to talk about what it actually means to be able to see infrared. So stick with this broadcast of Sci-Fi Overdrive. I'm the science giant Eric Landstrom. Hey, you can check out our website, www.sci-fi-overdrive.com, which is hosted by Detour.net. Detour.net, providing hosting services for the men, the women, and the hermaphrodites of the world. We're back on this broadcast of Sci-Fi Overdrive. I'm the science giant Eric Landstrom. Joining me in talking to our guest tonight is Lauren Urban, and our guest is Dr. Michelle Thaler, who is the manager for CERTIF, the Space Infrared Telescope Facility Education and Public Outreach Program. Now, one of the things about infrared, what is infrared? I mean, how is it more infra than just red?
Right. Well, infrared was actually named by William Herschel back in 1801, and infra means beneath, because he actually detected this light that was a little bit off the end of the red spectrum. He chose to call it beneath red. And beneath isn't a too bad description because infrared is a lower energy light. So it is kind of a below the energy of visible light, a longer wavelength. And we usually experience infrared as heat. That's sort of the most direct way that humans experience it. When something is warm, it's actually giving off infrared wavelength radiation. Now, when we say warm, I might mention that pretty much anything in the universe that's above absolute zero gives off a little bit of heat, a little bit of infrared. So a human body gives off a certain kind of infrared, a relatively high-energy infrared. But then you can go all the way out and look at very, very cold dust between the stars or very cold objects in the Kuiper Belt. These things could maybe only be, 30 degrees above absolute zero, very, very cold. But those also emit in the infrared at slightly lower energy infrared wavelengths.
Well, so here's my question, right? I mean, if we could see heat, let's be honest, humanity developed from a bunch of hunter-gatherers during an ice age, right? And if it was an ice age, wouldn't that have been a pretty practical thing for us to evolve, the ability to sense infrared radiation?
Well, it seems like eyes got invented a bit before humans did, though. There are very few creatures that actually use infrared eyes. In fact, nobody uses eyes the way we do. There are some things like pit vipers, like rattlesnakes, that actually have infrared sensors around their face, but they don't really image with them. It's more triangulation. So it seems like the sun, which is obviously our star, peaks its radiation. It gives off the most amount of radiation in visible wavelengths. And
Particularly in yellow.
Yeah, particularly in yellow-green. And for some reason, eyes on Earth really evolved to fit that wavelength peak. So nothing really sees in infrared. A bit unfortunate, except that the Predator alien, of course.
Yeah.
You guys remember that? That was able to see at infrared wavelengths.
So how was Herschel able to discover infrared radiation?
Well, it's just one of these, lovely accidents of science that, Herschel ended up doing this experiment all wrong, and he ended up detecting invisible light for the first time. What he did is that he was trying to see what the relative temperatures of the different colors of the solar spectrum were. So he got out a nice big glass prism, he projected a beautiful big rainbow, and then he put thermometers in the different colors of light. And then being a good scientist, he needed a control thermometer, one that actually wasn't in the light at all, just to take the ambient temperature of the room to sort of, make sure the experiment wasn't biased. And he put his thermometer right outside the red end of the spectrum. And that shot up higher than any of the other colors. So something was out there. He detected an invisible sort of light.
And that's how McDonald's learned how to keep your burger warm.
Sure
And
enough.
now you know the rest of the story. Actually, we're going to take a brief commercial break here. When we come back, now what I want to know is, so how does the Space Telescope process this image into something that we can understand? You're listening to a broadcast of Sci-Fi Overdrive. We're exploring the universe in the infrared part of the spectrum with Dr. Michelle Thaler. Do stay with us.
Sci-Fi Overdrive is back on Business Talk Radio with the weekly wild news of the week. Dateline London. Stonehenge murder mystery solved. Aliens did it. Scientists say that the discovery of an ancient mass grave at Stonehenge proves that space aliens built the mysterious monument with human slaves and then hit them with death rays to keep them from battling. The remains of 4 adults and 2 children were unearthed from the test site late last month. Tests show that the 6 people had been cut down in cold blood by what forensic archaeologists are calling surgically precise laser shots to the head. And that, say experts, was their reward for years of backbreaking labor that included pushing 20-ton boulders into a configuration that almost certainly served as an ancient air traffic control center for starships from another planet. We've long suspected that space aliens were deeply involved in the construction of Stonehenge as a beacon and landmark for UFOs. This mass grave proves it, declares Dr. Leonard Preston, founder and president of the Stonehenge Research Project. All that's left now for us to do is to find more graves with more bodies and more laser wounds. Only then can we begin to calculate what it took to build this monument in terms of human life and suffering. I want to know exactly what role humans played and what role extraterrestrials played. Were space aliens merely architects and masterminds, or were they involved in the actual moving and positioning of the stones? It is difficult to imagine humans moving those boulders without the help of machineries of some kind. It's true that they could have rolled them on logs and using poles and ropes for leverage placed them upright. It's also possible that highly intelligent beings from another world assisted with advanced technologies. We need more evidence, to be sure. The mass grave is the second mystery tomb to be unearthed at Stonehenge in less than a year. In 2002, the remains of a Bronze Age archer were found about a half-mile away, explains Dr. Preston, a forensic archaeologist who isn't directly involved with the excavations, but is widely considered one of the world's leading theorists. Everyone called the archer the King of Stonehenge because his clothes and other artifacts suggested that he came to England from the Swiss Alps and may have been the driving force behind the construction of Stonehenge. But now we can see that instead of a mastermind, he probably served in a mid-level supervisory capacity under the extraterrestrials. Perhaps these creatures brought him to England to supervise their human slaves rather than entrust a native Briton with learning too much about their techniques and purposes. It hasn't been widely reported because until now, nobody was quite sure what to make of it, but it appears that the Archer was murdered with a laser to the head, just like the others. Sophisticated radiocarbon dating tests are now underway to determine with pinpoint accuracy when the Archer and the other Stonehenge victims died. Meanwhile, they are presumed to have lived around 2300 BC, where the monument was built at Amesbury, 75 miles southwest of modern London. I believe these people deserve a moment of silence. Okay, moment's over. It's Sci-Fi Overdrive on Business Talk Radio, where we make fun of the long dead, only if they've been killed by aliens. Visit our website, www.scifioverdrive.com.
We're back on this broadcast of Sci-Fi Overdrive. I'm the science giant Eric Landstrom, and we're talking with Dr. Michelle Thaler, who is the Education and Public Outreach Manager for the Space Infrared Telescope facility. And we left off with this thought that it's possible to detect infrared radiation as heat. But what does it mean for the Space Telescope when it wants to take a picture of something in space?
Well, it's sort of an odd conceptual jump to think of heat as actually photons, as actually light. And that's sort of the difficult thing. I mean, obviously heat is just the motion of molecules. That's actually what heat literally means. But in human experience, when we think of something as being warm, it's actually radiating infrared radiation. That's actually what we detect as heat directly in our human experiences. So it's not too big of a jump then that if this really is light, it's just light our eyes are not sensitive to, then you could build a detector that is sensitive and translate that into an image that we can actually see ourselves. So every infrared image you're going to see out of this telescope will, of course, be false color. And there's all kinds of arguments among the scientists. I mean, should infrared always look kind of orange and yellow and red? Is that what the public expect? A lot of people say, why not use blue and purple and green? You're doing false color. So it's a challenge for us to figure out how we're going to present the images of space, because there's really nothing that our human eye would see.
And the agreement that you guys have come to is?
I don't know. I'm a little partial to the warm tones myself, but we haven't reached closure on this.
Is it all an aesthetic, or is there any kind of scientific precedent for that kind of thing?
Well, a lot of times you want to keep sort of the wavelength right, that a shorter wavelength infrared, even though that would seem very, very red, actually off the red end of the spectrum to us. Mm-hmm. If you're doing a false color, maybe you would color that blue compared to an even longer wavelength infrared. So if you're looking at heat coming from an object that's, say, 100 degrees above absolute zero, maybe that should look cooler or redder than the heat coming from something that's 300 degrees. So a lot of times they sort of try to keep that rainbow intact. They try to sort of keep our idea of a spectrum intact, even in a false color image. But there's no reason to do that. There's no real scientific reason for that. It just kind of makes interpretation a little bit easier.
And this brings us to the nickname, or I guess the motto that the Space Infrared Telescope facility has got, the search for the old, the cold, and the dirty.
That's right.
Which refers to what?
Well, all the things that infrared is really, really good at picking up. I mean, let's start with the old. You've probably heard of the redshift, that when you look at galaxies very, very far away, we're talking billions of light years now, the light is actually lengthened in wavelength as it travels through the expanding universe. Things are shifted towards the red end of the spectrum. And it makes sense then that if you look really far out into space, things would get shifted all the way out of visible light entirely and into the infrared. So what we're saying is that there's a galaxy, let's say 13 billion light years away, and light left that galaxy 13 billion years ago as, let's say, ultraviolet light, really, really nice blue energetic light. But it had to travel through all of that expanding space between us and the galaxy. And the wavelength got stretched out all the way down past orange, yellow, red, all the way past visible into the infrared. So in a very real way, you can actually see farther out into the universe, and that means farther back in time using infrared. We're hoping to detect some of the very first galaxies when light was really just beginning to come out of these billions of years ago.
So what you're talking about is essentially like there are invisible stars and invisible galaxies that they exist. It's just that their wavelengths have been so stretched out that we don't see them as being red giants anymore.
Exactly. They're totally invisible to us.
Wow. Invisible universe and galaxies. Hey, we're going to get to the cold and the dirty once we're back from this commercial break. Keep listening to Sci-Fi Overdrive. Back on this broadcast of Sci-Fi Overdrive, and we're continuing our conversation with Dr. Michelle Fowler about the Space Infrared Telescope facility as it searches for the old, the cold, and the dirty. Dr. Thaler, we've done the old. Tell us about the cold and the dirty.
Okay, well, the cold should be kind of obvious. Like I was saying, anything that has any temperature at all, anything that's above absolute zero, will be detectable in the infrared. It's giving off some heat. So things that are too cold to be giving off any visible light, like there's lots of dust drifting around between the stars that we normally don't see at all. It's very cold, not radiating any visible light that we can see. It's radiating plenty of infrared. So you can map the larger structure of all the gas and the dust in our galaxy and other galaxies as well. There's also things like asteroids or really big balls of ice out in the Kuiper Belt, things that are almost as big as Pluto. These things would be so dark in a visible light telescope you'd never see them. But in an infrared telescope they would glow wonderfully. We're hoping to find lots and lots of new solar systems because the warm dust that's left over from when planets form should be detectable by SIRTIF. Now, that's the cold, so pretty much anything with a temperature we'll be able to see, even if it isn't glowing in visible light. The dirty is a little bit different. A lot of people don't know this. Infrared has this great property that it can actually cut through dust and smoke and little kinds of particles like that. Firefighters usually use infrared cameras to actually find where people are trapped inside smoke-filled buildings. You can just see right through the smoke like it wasn't even there. Now, in the case of space, there's all kinds of neat things that go on inside giant clouds of dust, and the dust is so thick it blocks all the visible light. To me, one of the most exciting things that we're going to see is that star and planet formation takes place inside these giant clouds. You guys have seen that beautiful image from the Hubble, the Pillars of Creation. And
the Eagle Nebula, right?
Yeah, the Eagle Nebula. I love that one. Well, there are actually lots of stars forming inside those dust clouds that you can't see. And when you map that region in the infrared, you can just cut right through the dust and see where the new stars and planets are forming.
Excellent.
So that's the dirty, the dusty stuff. Things like black holes. Black holes accumulate lots of stuff around them. Their intense gravity sucks in lots of dust. And if you want to look down close to where the event horizon is, where things are actually falling into the black hole, you need to cut through all that dust. So SIRTIF should be great for studying some of these giant black holes that power the very active galaxies.
So this is another way of finding more of that, the stuff that the universe is made of that we can't necessarily see. I mean, I've always heard about when we're looking out into the universe that what we're actually seeing is, 5% of what's really there, and this is just another way of being able to see all of that.
Well, unfortunately, things are even weirder than that. A lot of people think that SIRTIF is detecting that stuff called dark matter because we say things that, okay, we're seeing things that don't give off any visible light. But it's really something different. Dark matter is actually, we believe now, not made up of atoms like any other matter in our universe, not made up of atoms at all. Because when we say dark matter, we mean that it doesn't emit in any kind of wavelength. Dark matter does not emit at infrared or at gamma rays or at radio or anything. And nothing made of natural matter, good old, protons, neutrons, and electrons can do that. Everything, even if it's only a fraction of a degree above absolute zero, it'll emit a radio wave. Things do not get away with not emitting any kind of light at all. So the dark matter is even more mysterious. Whatever it is, it's not made of the same stuff we are. And everything that SIRTIF is going to be detecting, like stars and planets and distant galaxies, that's the same stuff we are. That's made of atoms. So we're still dealing with only the tiny little 5% or so of the universe that's made of regular matter. We're actually not detecting dark matter.
Yeah, but dark matter still exerts gravitational attraction, right?
That's true. So with some of the galaxy surveys, we may actually be able to see where the dark matter is pulling on the galaxies.
And if it's pulling, that means stuff is moving, and you told us that motion evidences itself as heat because that would be kinetic motion, right?
Well, motion of molecules in that case. I don't know about bulk motion. So dark matter is even weirder. We have lots of theories now for what dark matter may be, but I think we're going to have to wait probably a couple decades until we get a better handle on that.
Well, so give me a sort of sense here what we can actually look for. I mean, comets coming into our solar system or just extragalactic stuff?
Pretty much all of the range there. I mean, we're going to be doing some studies of the solar system. There are objects we're now discovering out in the Kuiper Belt that I mentioned before that are pretty much close to the size of Pluto. The biggest one is called Quar. And so there are probably relatively large bodies in our own solar system we haven't found yet. We'll be looking at lots of asteroids, looking at lots of the dust that surrounds our solar system. So we're going to go from studying objects in our own solar system, finding things way out in the cold reaches of our solar system, all the way out to the most distant galaxies that we can image. So there's a huge range in the subject matter we're going to study. The neat thing about SERDIF is that it really wasn't a very directed science mission. It has very specific science goals. But what I mean by not directed is that we're obviously going to be discovering some things that we're not expecting. And SERDIF has plenty of time to follow up on observations, to look at things a couple of times and see what's happening. It really is a true explorer. It's not just set out to answer one question. It's setting out to answer a whole range of things.
So going off on a slightly different tangent here, you are the manager of the Education and Public Outreach Program for SERDIF.
That's right.
What does this job entail? And you know, besides coming on our wonderful radio program and telling us all about the SERDIF, what else is it that you do?
Oh, well, like everybody, I guess my job is about 90% red tape. When you try to manage a program, you're always doing budgets and schedules.
It's infrared tape.
That's right, infrared tape. Yay.
Well, no, we can see this tape.
Actually, you know, our softball team is called the Infrared Sox. But no,
oh, man.
In all seriousness, NASA is getting very, very committed to putting a lot of energy into education. There's kind of a frightening lack of young people going into science these days, and NASA's a little scared about that. It looks like it's not really going to be able to replace all of the people that are retiring. And so I think NASA's mission always has been to get the public involved in science and get them involved in the excitement of discovery, but now it's getting a bit acute. Now it's sort of, okay, if we don't do this well, NASA may cease to exist because we don't have enough scientists and engineers to run it. So really, in the last few years, there's been a big push. There's been a good amount of money put into it. And we do everything. We do a huge range of things. We have programs that get master's degrees for teachers in science education, because we found out that a lot of people that are trying to teach science in the public schools don't really have any formal science background themselves. We go out to schools. We talk to students. We do teacher workshops. We design planetarium shows and museum displays, and our website that the public will be able to access data, do what they like. We'll also be initiating a program where teachers and schools can use time on SERDIF, and they'll probably work with an astronomer on a project, and then the students will actually get to select which things they'd like to look at with the telescope.
The non-classified stuff, of course.
Oh, yeah. But there's a huge range of programs that I try to manage, lots of different things.
Excellent.
You mentioned a website. Go ahead and let's hear it.
Okay, well, do come see us. The main website for the mission is sirtif.caltech.edu. So that's SIRTF.
As in Space Infrared Telescope Facility.
Got it. .caltech.edu. Well, we also have a new education website called Cool Cosmos, because infrared is cool and infrared sees cool things. And so you can also go to, I believe that would be coolcosmos.ipac. IPAC, which stands for Infrared Processing and Analysis Center, .caltech.edu. Or just do a Google search on Cool Cosmos and you'll find us.
Okay.
Outstanding. And, you know, you mentioned 2.5 years as the life expectancy on it, and I know you said plenty of times, but let's be honest, we're looking at the success for a Hubble Space Telescope. I'm sure you guys are planning for the next Space Infrared Telescope facility. We're back, and we're finishing up our conversation on Sci-Fi Overdrive with Dr. Michelle Thaler. Doc, you were talking before about the shortage of getting students today interested in the hard sciences, and let's be honest, if I'm going to stand in front of a bunch of students and say, yes, most of the universe is entirely non-interactive dark matter, and we have no idea what it is, you can understand their confusion. So what I want to do...
That's so cool.
What I want to do is take this opportunity and show a little bit more of the human side behind science. On your profile page, there's a great picture of you in visible light and a picture of you in infrared light next to it. And then there's a picture of you in Elizabethan garb.
Yeah, it's strange but true, yes.
Yeah, go ahead and tell us what you do. You mentioned the softball team, the Infrared Sox. Tell us a little bit more about what you do when you're not being brilliant.
Well, I always loved Renaissance fairs when I was a kid growing up, and when I came out to California, they have quite a wonderful Elizabethan reenactment out here called the Guild of St. George. And so both my husband and I joined their dance troupe, and also we sing madrigals in their choir, and then we have to, during the fair, just portray characters in Elizabethan England. So we have great fun doing that on the weekends. We also perform at the Getty Museum and the Huntington Gardens. So a lot of the museums around California, you can find us there.
And you're also at the Santa Barbara Renaissance Fair?
Yes, on the Santa Barbara Renaissance Fair,
Hmm.
A lot of fun. Actually, the picture on the website that you see of me there is my wedding picture. So normally I look even a little bit more authentic than that. I have a bridal veil on and my hair's down. But if you'll notice, that was all in black.
Yes.
We found out that Elizabethan brides would have worn black. That was the most ostentatious color because you needed to use a huge amount of indigo to actually dye fabric that dark. It was very expensive. So we got married in a Scottish castle, all in black.
Wow, hey, so this is something completely different than the science side, which must be nice, you know. Do the two ever meet? Do you find yourself at a Renaissance festival talking about infrared light, or?
Oh, all the time. We were not necessarily infrared light, but we were showing people how to do things like sight the sun with an astrolabe, and how you can read the time, how you can figure out your latitude. There's a lot of astronomy you can incorporate in because the Elizabethans were great navigators, really good sea people, and so we would do a little bit of that. Unfortunately, portraying an Elizabethan woman. Elizabethan women would have known some astronomy because astronomy was considered one of the basic liberal arts at that time. So if you were a well-educated woman, chances are you had actually done some astronomical measurements and some theoretical calculations. But there weren't a whole lot of women on the ships doing the actual navigation.
I can imagine.
Maybe. We don't really know, but probably not.
But, I mean, considering that Galileo Galilei created the first telescope in 1608, what evidence is there of Elizabeth I or James I as being a possessor of a telescope?
There were people in their court. For example, there was John Dee in the court of Elizabeth who had lots of telescopes. John Dee was considered a scientist at the time, and he actually was quite an advocate of the heliocentric solar system. So Elizabeth would have been aware that somebody had proposed the idea that the sun was in the center of the solar system. And the Elizabethan court actually made a point of kind of pissing Italy off by accepting it more readily. So while Galileo was busy getting persecuted in the reign of James, things were a little bit easier in England, and it was kind of a way of thumbing your nose in Italy. So neither Elizabeth nor James were great scientists themselves, but they had scientists in their court. Actually, if you care to call them that, John Dee also gazed into crystals and talked to angels. And I believe James ended up executing him for sorcery.
Whoops.
Yeah, well, I mean, Isaac
The
Newton.
definition of science is a little fast and loose.
Isaac Newton made a great living casting horoscopes and doing that. But see, this is the sort of stuff you learn by hanging out with Rennies.
Yeah.
We've been talking this hour of Sci-Fi Overdrive with Dr. Michelle Thaler, the manager for the Space Infrared Telescope Facility Outreach and Public Education. Thanks so much for joining us.
Thank you.
This is Sci-Fi Overdrive on Business Talk Radio. We'll be back with more science after this. Science! Sci-Fi Overdrive is back in our final hour here on Business Talk Radio.
Aww.
As we continue boldly going into the great beyond and other great cliches like that. Eric, what are we talking about now?
No, I got to tell you, if you are into hard science fiction, this is the hour to listen to. We're talking with Professor Lynn Kaminsky, who's doing the Gamma Ray Large Area Space Telescope. We are going to be talking about gravitational waves. We are going to be talking about supermassive black holes. We are going to talk about colliding neutron stars. We're going to be talking about what gamma ray exposure does to your body.
It does not turn you
It does not turn you green, but it does turn you blue, and you'll find out why in this hour of Sci-Fi Overdrive.
We're bringing you all sorts of stuff that's probably going to kill you and wipe out all life on Earth as we know it.
Ozone, at least. Ozone.
On Sci-Fi Overdrive on Business Talk Radio. Visit their website, www.businesstalkradio.net, where you can find out about our show and dozens of other interesting shows. And then when you're done with that, come by our website for all sorts of fun games and weird pictures that I get bored and doing Paint Shop Pro. It's sci-fioverdrive.com.
Thanks for tuning in Sci-Fi Overdrive, America's premier weekly radio program about science fiction and science facts, stranger sounding than fiction. On this show, we've been talking about the universe and the Enderverse, and now joining us by telephone is Dr. Lynn Kaminsky. Dr. Kaminsky joined the faculty at Sonoma State University back in 1986. She's been the professor of physics and astronomy since 91. In 1992, Dr. Kaminsky began collaborating with scientists in the particle astrophysics group at the Stanford Linear Accelerator Center and at Stanford University. When the Sanford Large Area Telescope was selected by NASA in 1999 to be the primary science instrument on the Gamma Ray Large Area Space Telescope, Dr. Kaminsky was chosen to lead the education and public outreach program for the mission. She joins us now to talk about gamma radiation and why it won't turn you into the Incredible Hulk. Welcome to this broadcast of Sci-Fi Overdrive.
Thanks. I'm glad to be here.
It's a pleasure to be able to talk to you, especially considering in our last hour we were talking with Dr. Thaler about the successful launch of the Space Infrared Telescope facility. So I guess my question is, we were talking about how infrared radiation is this long radiation and it seeks out things that are much cooler. Why do we need a gamma ray telescope in outer space?
Gamma ray telescopes look at pretty much the entire opposite end of the electromagnetic spectrum. We're the real high energy folks, the real high energy radiation. And gamma rays come from the most exotic and violent objects that are out there. Infrared comes from things like stars and cool stars and stars that are just being born. Gamma rays come from things that are exploding and jets that are flaring and supermassive black holes, things that you can't really study in a laboratory.
Well, we got a science fiction audience that's listening to us right now. So, really go in depth with us. When you say stars exploding, what would make, when a star explodes, produce gamma rays?
Most of the gamma rays that we see are actually not from thermal matter, which is matter heated up to a certain temperature. When you're looking at infrared, you're seeing matter that's heated at a certain temperature, like our bodies radiate infrared. I'm sure Michelle talked about that.
Mm-hmm.
But in order for something to emit gamma rays, to be hot enough to emit gamma rays, it would have to be billions of degrees Kelvin.
Whoa.
Okay, so not very many things in the universe are actually at billions of degrees. The only time when things really get that hot are occasions when things blow up, like, say, the very beginning of a supernova. Okay, so that's one place where you get gamma rays. In fact, on Earth, where people saw gamma rays is when they exploded atomic bombs.
No.
Okay, but that's, one of the few
That would
places
be the
where you've
extreme
gotten
example. Right.
thermal gamma rays. Now, you can make gamma rays other ways where you don't have to heat matter up to billions of degrees, and those are called non-thermal gamma rays. And most of the gamma rays that we see in the universe are coming from things that are not billions of degrees, but are things with super strong magnetic fields, for example, or particles, elementary particles like you'd have in an accelerator, like at SLAC, the Stanford Linear Accelerator Center. You can have particles accelerated up to speeds very close to the speed of light, and they will produce gamma rays also.
That's 186,000 miles per second?
Right.
Or to be metric, 300 million meters per second.
For our friends in Canada.
Yes.
So most of the gamma rays that we see from objects in space are non-thermal gamma rays that are coming from accelerated particles and jets, say, being shot out of supermassive black holes that are billions of times the mass of our sun. Or we see gamma rays that are made when charged particles are accelerated by spiraling around really strong magnetic field lines from, say, a neutron star that has a magnetic field that would be 10 to the 12 Gauss, which is, 1,000 billion Gauss. Our Earth's magnetic field is a half of a Gauss.
Whoa.
Okay, so if you go to a neutron star, you have this incredible magnetic field. And if the neutron star is sending out jets of particles, those particles will spiral around the field lines, and they can produce gamma rays as they're accelerating in these curved orbits.
So is this the only way to study some of these objects, like the supermassive black holes and everything?
Well, it's certainly one of the most popular ways these days. Now, this is a big surprise to everybody that the supermassive black holes, so many of them, would be shooting jets out. As you know, of course, black holes are very famous for sucking in everything.
Yeah.
Right? So it's quite the mystery how the black holes, which normally would suck in anything that would come across their event horizons, can somehow, because they're spinning around and because they have magnetic fields outside their event horizons, twist up the magnetic field lines and end up making these beams of particles that are getting shot out, and the particles are accelerated up to close to the speed of light. That's something we'd really like to understand. And the best way to understand that is to study these galaxies, they're called active galaxies, is to study them in gamma rays.
Okay, I guess my question is, why have a space telescope? You said that we've seen these thermal and non-thermal gamma rays, so we must have been able to detect it before, right?
Right, with other spaceborne telescopes.
Okay, and that would include
and I guess
the Compton.
I missed the part about how the gamma rays don't get through the Earth's atmosphere, and so you have to go to space to see them.
Ooh, how come they don't come through our atmosphere?
Well, actually, we wouldn't be here if they did.
Good point. That it would be like an atomic bomb blast now in retrospect.
So we're actually very, very glad about that. Some of the very, very high energy gamma rays, once you get above, the typical energy of the gamma rays that GLAST is going to study are gamma rays that are 100 million electron volts and more energetic. Once you get above 100 billion electron volts, the gamma rays, when they come down into the Earth's atmosphere, will interact with molecules in the air and cause showers of blue visible light, actually called Cherenkov radiation. You can detect that on the ground, and so you can study this really super energetic, ultra-high energy gamma rays with ground-based visible light detectors. But between 100 million and 100 billion electron volts, those gamma rays don't have enough energy to make these showers that you can detect, and so they don't make any signal down at the ground that we can see. They just get absorbed by molecules and not much else happens. But that's very lucky for us, of course, that is true. Otherwise, they would have fried all the living creatures at the beginning of life on Earth, and we wouldn't be here.
Yeah, actually, as I think about it now, I recall when they removed depleted rods from nuclear power plants, like the one in Port St. Lucie, and they put them into the storage, and they have a boron solution in the water. You see them with that eerie blue glow that you always think, oh, that's radiation for you right there.
Right, and it certainly is. And it's not very good to be around the spent fuel rods either.
Remind me to cancel that trip the next time I wanted to go.
Yeah. Although, actually, that does make me wonder, so why do people always think gamma radiation makes you green? Yeah. Well,
the Hulk, of course, is the most famous being that somehow is affected by gamma rays. The reason I think that gamma rays have, this reputation is because as a form of ionizing radiation, like X-rays as well, they have the ability and the very short wavelength to penetrate inside cells and cause mutations. But mostly the kinds of mutations they cause lead to cancer, and certainly there have been lots of studies of the atomic bomb victims, and that whole thing has been documented, how much of a dose you get and how much that increases the chance that you get cancer, things like that. There are no documented cases of people turning into the Hulk, or, and somehow when he gets really big, he manages to keep his pants on. I've never understood that part.
That's the censors right there.
I was about to say, that would be the comic book authority.
Yeah. But there are no documented cases of people changing form, just individual cells being able to be mutated.
But I mean, gamma rays cause stars to change form, right? I mean, we're looking at the supermassive black holes, which would only be found at the very center of galaxies because they have masses billions of times in excess of our own sun.
That is where the active galaxies are formed, that's true. And the jets that are shooting out of them, the ones that we detect gamma rays from, is when the jets are aimed right at us.
But by the does the Milky Way have a supermassive black hole in the center?
It has about a 2.7 million solar mass black hole, but as far as we know, it's not shooting out.
We're back on this broadcast of Sci-Fi Overdrive. I'm the science giant Eric Landstrom, and I'm joined by
Lauren Urban, who is just not a science giant. I'm sorry.
Yeah, but we are talking about gamma radiation, and apparently if we expose it to you, it won't turn you into a large rampaging creature. Well, it'll only give you cancer and make you die.
Oh, darn.
But here's the interesting thing. Because cells get destroyed when they come into contact with gamma radiation, we've been talking with Professor Lynn Kaminsky from Sonoma State University about what sort of instruments would be necessary to pick up these gamma ray bursts that are coming from black hole. And she was going to tell us about the Gamma Ray Large Area Space Telescope, also known as, by the initials, GLAST.
Well, every NASA mission almost has to have an acronym, and so GLAST is ours.
Mm-hmm.
It was originated in the time when we were becoming friendly with the Soviets, and we thought maybe that would help get funding. But here it is, back in the days of glasnost, remember that? But here we are, and we're looking at a launch in about the end of 2006. GLAST has two main instruments on board. One is called the Large Area Telescope. That's being managed by Stanford University, and is being built by an international collaboration which includes institutions from Italy, France, Japan, and Sweden.
But no Russians.
But no Russians, as it turns out. And it is also has funding in the U.S., not just from NASA, but from the Office of Science and the Department of Energy. So it's the first time that there's really been a collaboration within this country between the astrophysicist funded by NASA and the particle physicist funded by the Department of Energy.
Fantastic.
So that was an interesting cultural study in and of itself. The reason the particle physicists got involved is because the detectors and the technology that's used in the Large Area Telescope has a heritage in instruments that were designed to be part of large particle physics experiments, such as the superconducting supercollider, which got canceled a few years back.
That was the one in Texas.
That was the one in Texas.
Okay.
And the way that the Large Area Telescope works is the gamma ray comes in and converts into a pair of particles, an electron and a positron, which is the anti-particle of the electron.
Oh, antimatter.
Right, antimatter, by hitting some converter material, which is usually lead or, in our case, tungsten. And so once you have this conversion, those two particles travel through the rest of the telescope, which is made of interleaved layers of this converter material and silicon strips. And the silicon strips track the path of the particles, and when it gets down to the bottom and it's gone through all the tracking material, they deposit their energy in big chunks of cesium iodide, which act as a calorimeter to measure the total energy that was in the shower. And so then you use a computer to work all that backwards, starting from the energy in the shower, trace the tracks back up, and you can basically make what's called a pair conversion telescope. It tells you where the gamma ray came from that converted into the pair.
Now, when you say a shower, what are we looking at?
Well, it's the shower of the particles as they go through the different layers.
Right, but I mean, an electron has got 9.11 times 10 to the negative 31st grams worth of mass. So how much matter, how much antimatter for that matter, are you being hit with in a shower?
Right. Well, basically, that's just its rest mass, right? It also has all the kinetic energy that it got from the gamma ray, from the conversion process, right? So the gamma ray is just an electron's rest mass in electron volt units is 511,000 electron volts. Okay, 511 keV. So a half an MeV, and these gamma rays are 100 MeV. So they have something like 200 times or more as much kinetic energy as they have rest mass energy. And you get to see all that energy in the particles when they land in the calorimeter, in the cesium iodide crystals at the bottom of the detector.
Yeah, so really you only need to be hit by, like, what, one or two gamma rays then?
Right. Well, gamma rays are fairly rare, which is, another thing that's good for us. But we get a lot more background signals from other charged particles that are in orbit around the Earth than we actually see signals that are generated by the gamma rays.
Okay, we're going to take a break, and we're going to talk about the placement of this gamma ray large area space telescope, where it's going to be in space. Once we come back from this brief commercial announcement, you're listening to Sci-Fi Overdrive.
Sci-Fi Overdrive on Business Talk Radio. It's the bottom of the hour, so you know what that means. It's time for the weekly world news. Not as good as David. World news of the week. Dateline, somewhere. Amateur astronaut builds his own spacecraft and plans to pilot it into space. Yep. Maverick rocket buff Steve Bennett has set his sights mighty high. He's determined to become the first amateur astronaut to fly into outer space and back in a privately built craft. For the past decade, bold Bennett, age 39, has been doggedly building huge rockets in his sprawling workshop, and he successfully launched at least 11 of them in pursuit of his way-out dream. The intrepid Englishman, founder of his own private space industry called Star Chaser Industries Limited, told reporters, quote,
The space race is back on, and we predict that a global space tourism industry worth $10 billion will be the big business of the early 21st century, end quote. Bennett made headlines worldwide 2 years ago when he launched an unmanned prototype named Nova from Morecambe Bay. The 37-foot rocket, weighing 1,643 pounds, was able to zoom from 0 to 500 miles per hour in just 6 seconds, a dazzling feat that has convinced many scientists that the British Buck Rogers wannabe may not be crazy after all. Bennett declares, and I quote, "We've proved the design of the rocket and capsule both on paper and in the air. It's now time to show the world that we mean business and move into the man phase," end quote. This year, Bennett's efforts have focused on tests of his manned Nova 2 capsule, including dropping it from a C-125K transport aircraft at 14,000 feet, giving him a chance to practice land the reusable craft. Brave Bennett does all the test piloting of his homemade rocket ships. He says, quote, "I've dreamed about flying in one of these rockets since I was 5, end quote. The $83,000 U.S. craft was paid for with the help of a variety of sponsorships. Bennett, director of the Space Technology Laboratory at Salford University, hopes to win the coveted X Prize, set up by a foundation in St. Louis in 1996 to promote private space exploration. A $10 million cash prize is up for grabs for the first non-governmental group to fly 3 people 62 miles up into space and then safely back down. The father of 2, whose devoted wife Adrienne supports his space pioneering efforts 100%, has vowed to do just that in the craft he's working on now. It's called the Thunderbird Rocket and Capsule. Bennett describes it as, quote, "a single-stage system designed to carry ordinary people on short suborbital flights, pleasure flights into space," end quote. The first manned test flight is scheduled for August of 2003, which means it's already happened by now. So we will keep you posted and let you know what's going on. And Bennett plans to boldly go into space and seize the X Prize by 2005. This is interesting, especially since he's called it the Thunderbird. Thunderbird is go. Well, one of them, anyway. By the way, the website here for this is www.starchaser.co.uk. www.starchaser.co.uk. So check it on your website, and hopefully there's no 404. And that is a look at the weekly world news of the week on this broadcast of Sci-Fi Overdrive on Business Talk Radio. Hey, you, yeah, you. Check out our website, won't you? It's www.scifyoverdrive.com. And yeah, we're on the Business Talk Radio Network Monday mornings from 2 a.m. to 6 a.m. Eastern Time. Check out their website, by the way, won't you, too? It's www.businesstalkradio.net.
We're back on this broadcast of Sci-Fi Overdrive talking about GLAST, the Gamma Ray Large Area Space Telescope, which is designed to detect gamma rays as they become both matter and antimatter in space, letting us know the location of supermassive black holes and super strong magnetic fields around neutron stars. Pretty spacey stuff, huh?
Yeah.
Here's the question, though. Speaking of space, though, you mentioned, Dr. Kaminsky, that it's going to launch in 2006. What kind of rocket are you using? Are you dependent on the space shuttle to get it up? Are you using an Atlas? Are you using a Delta II? And where is this thing going to be in space? Is the space shuttle going to be able to fly up to it and service it like the Hubble Space Telescope gets serviced?
Most of the NASA missions in sort of the post-Hubble era have gone up on rockets, and GLAST is no exception. It's going to be launched by a Delta rocket into basically a 28.5-degree inclined orbit, which is the orbit from Kennedy. And it will be at about 550 kilometers, so it won't really be reachable by the shuttle. For repairs, it's designed to last for 5 years with a hope for a lifetime of 10 years.
Mm-hmm.
So we hope it'll be up there for 10 years. Also, another new thing, since the demise of the Compton Gamma Ray Observatory, which was the last really big gamma ray satellite that was up there from 1991 till the year 2000, they purposefully deorbited Compton because it had one of these big heavy calorimeters on it, as well as other parts that wouldn't break up into small chunks on re-entry. So they were worried about it falling over some part of land where there would be people. And so since then, all big heavy satellites like GLAST that have big chunks of heavy material like the cesium iodide have to have the ability to do a controlled re-entry. So one of the things we're still studying in the spacecraft design is exactly what kind of propulsion mechanisms are going to be put on the satellite either to keep boosting the orbit or to help boost the orbit and then help control the reentry when the mission life is finally over.
On a total tangential question, I mean, since it's, being exposed to antimatter and it's designed to detect gamma rays, would GLAST become radioactive itself to some degree?
Not noticeably, no, because the positrons are not really like fast neutrons or other things that tend to make material radioactive and change the material. They're just positrons. They're little wimpy things. Most things, for example, in nuclear reactors that become and stay radioactive, it's because they've been hit with fast neutrons, so really energetic neutrons.
Now, you were chosen to lead the education and public outreach program for this mission. Just briefly, what are some of your duties as in this office?
We have a very large program that we're in the middle of doing with GLAST. We produce materials for K through 12 schools, mostly concentrating on high schools. We have a beautiful poster about active galaxies, for example, that goes with an educator's guide with activities to do in the classroom that just came out. If people go to the glast.sonoma.edu website, they can see some of our products and even see an order form for how to get some of the things that my group has produced. We're currently working on plans for a PBS Nova show about high-energy astronomy.
So stay tuned for that.
Yeah, so that will air in probably late 2005, so that's very exciting.
One more time, let me get that website.
GLAST, G-L-A-S-T, .sonoma, SONOMA.edu.
We're talking with Dr. Lynn Kaminsky. When we come back from this brief commercial announcement, we're going to talk about SWIFT, which is another exploration of high-energy astrophysics. So keep listening to Sci-Fi Overdrive, and we'll increase your brain power right after this brief commercial announcement. We're back on this broadcast of Sci-Fi Overdrive. I'm the science giant Eric Landstrom, and we've been speaking by telephone with Dr. Lynn Kaminsky, who's the head of education and public outreach for some high-energy astronomy being conducted by the GLAST mission, Gamma Ray Large Area Space Telescope, and SWIFT. Dr. Kaminsky, what is SWIFT?
SWIFT is one of the only NASA missions that's not an acronym, actually. It's named after the bird, the swift bird, which can very swiftly turn while it's flying and catch insects. And the idea for the SWIFT satellite is that it can very quickly spin around in orbit and catch gamma ray bursts. And so SWIFT is a medium-sized explorer satellite. It's quite a bit smaller than GLAST. It, too, will be launched on a Delta rocket. We were hoping for launch early in the year 2004. It's looking like something like maybe February or March.
Now, when you say turn swiftly, how does it do that?
It has lots of big reaction wheels in the satellite that just got declassified, so SWIFT is one of the first satellites that has used this military technology. And when its large area burst alert telescope sees a gamma ray burst go off, it will spin itself around in less than a minute to focus its smaller area field of view detectors that are ultraviolet optical telescope and X-ray telescope on the field of view with the burst so that it can get simultaneous information about the gamma ray burst in other wavelengths.
I guess what is a gamma ray burst?
Gamma ray bursts are the biggest explosions that happen in the universe today. They're the biggest things that happened since the Big Bang, the explosion that started the universe.
So we're talking beginning of the universe kinds of astronomy and science.
Well, we'd very much like to understand what they are. They were first discovered in the year 1967, so they've been a mystery for over 30 years now. They were discovered, in fact, by satellites that were sent up to look for violations of the Nuclear Test Ban Treaty. The satellites were called Vela, which means watchers. And they were looking for gamma ray explosions on Earth, and what they found were gamma ray explosions coming from space.
Anywhere in particular?
Well, that was what it took a really long time to figure out. In the beginning, the amounts of energy that were hypothesized to come from these bursts seemed so large that people thought they must be from within our own galaxy. That turned out not to be true. In 1997, an Italian-Dutch satellite named BeppoSAX finally found the first afterglow of a gamma ray burst. Now, you'd think that if something was blowing up, it should leave some glowing embers behind.
You'd think.
And so people were looking for those glowing embers at wavelengths that represent less energy, like X-rays or visible light. BeppoSAX found the first X-ray afterglow in 1997, so 30 years it took after the original discovery of gamma ray bursts for a satellite to find evidence of this blown-up thing at some other wavelength.
Okay, but why? Why 30
Basically,
years?
because it's very difficult to figure out where gamma rays are coming from. You can't make a very good gamma ray telescope. The gamma rays go right through glass. It doesn't work like a normal telescope. You can't focus gamma rays. The best you can do is the pair conversion telescope that I told you about before, but that only works for gamma rays that are over about 100 million electron volts.
Right.
You have to have enough energy to make the pairs. The gamma rays in the gamma ray bursts are more like 1 million electron volts. So there's no really good way to position them, and it usually takes triangulation between a lot of different satellites in the so-called interplanetary network to come out with the position, and that takes days. And by that time, the glowing embers have faded, and you can't find them anymore.
And that's why you need SWIFT, something that can,
Right.
within 1 minute, pivot and take a
Go
look.
over there and look at that spot. Now, since the breakthrough discovery by Bepisax in 1997, there have been probably 20 or 25 bursts that now have optical counterparts. Some of them were done with using data from Bepisax. A lot of the recent ones have been done using data from the HEDI satellite, which is a little tiny satellite that is a NASA satellite that's up there right now and still working. SWIFT is much bigger than HEDI and will have a longer lifetime, hopefully, and will be able to look at X-ray and optical simultaneously. HEDI concentrates on sending the position down to the ground within seconds and then getting people on the ground to look at these bursts with their telescopes.
Now, I mean, you must have some idea, or someone at Sonoma State University must have some idea where gamma ray bursts come from. I mean, Steve Hawking talks about black holes evaporating, is that sort of thing?
Well, that was actually an original theory for something that could make gamma ray bursts, was a primordial mini black hole evaporating. But that's not what the evidence is pointing to. What most of the current evidence points to is the explosion of about 100 solar mass star in what we call a hypernova, which is bigger than a supernova, and astronomers like to hype things, and so we had to come up with a thing that was a supernova, right? So it became a hypernova. So if a star like that explodes, the core of the star could collapse all the way down and become a black hole immediately. Whereas, say, if a 30 solar mass star explodes in a supernova, you'd get a neutron star, or maybe a black hole out of it, but mostly you'd make neutron stars. We think that the extra energy that you see in a gamma ray burst that makes it much more energetic than just a supernova is because you get this collapse that goes all the way down to form a say, 10 solar mass black hole, or maybe larger. But it's hard to have stars much more than 100 solar masses. They would live a very short life. You would have them in all sorts of different galaxies. Gamma ray bursts never are seen to come from the same place twice. And now that we have some good positional information from these optical afterglows, it looks as though, in a lot of cases, the bursts are located in the star-forming regions of the galaxies. So that gives credence to this idea that it's a very short-lived, very massive star that's just blowing up. And we're seeing the birth of a black hole every time we see a gamma ray burst.
Let me spitball this for you a moment. The Orion Nebula, okay, it's about 1,500 light years away from us, right? And that's a star-forming region of space.
Yes, it is.
What would happen if we had a hypernova go off in our quote-unquote neighborhood within 1,500 light years?
Well, there have been a few people that have actually done studies about this. If you have something at about 1,500 light years, the first thing that would happen is that you would have ozone depletion from the gamma rays interacting with the molecules in the air. So then, you'd have a worse ozone problem than we have now, and so you'd have a lot of excess cancers.
Yeah.
Okay, it would be sort of, the scale of a really large volcano or a really bad solar flare or, like, say, a really big meteor impact. But if you got to, say, 300 light years away, and we don't think that there are any big stars that close that we'd be able to see them, you could end up wiping out the entire ozone layer.
Oof.
And that would have very big consequences from the Earth. You'd also get radioactive nuclides. You'd get fallout all over the world. You'd have, sort of a nuclear winter from the nitric oxides that would be formed, acid rains. It would be very bad.
The reason I ask that, we've had, mass extinctions occur here on Earth since we got multicellular life about 1 billion years ago. Has this thing ever happened in the Milky Way galaxy? Do we see any evidence of those nuclei?
Well, we haven't been able to tell that any of our own mass extinctions have been caused by gamma ray bursts, although I did have some geology students do a project on that, looking into it to see whether gamma ray bursts could be associated with some of the mass extinctions. The dinosaur one, I think it's pretty clear, came from an asteroid impact, and they're going to be a lot more common than a gamma ray burst in our local neighborhood, but you certainly can't rule it out.
Well, I just want to know that when we wipe out our ozone layer, it's us doing it, not a hypernova going off.
Well, the gamma ray bursts that have been seen to be associated with the hypernova are the gamma ray bursts that last more than 2 seconds in the gamma rays. There's another class of gamma ray bursts that are less than 2 seconds long, and we don't really know what causes them, but one leading theory is that you have a binary neutron star that's the two neutron stars are spiraling around each other, and when they finally collapse into each other and form a black hole, they put off a big burst of gamma rays. Oh. It is possible for binary neutron stars to be closer to us than a star-forming region with a 100 solar mass star, because it's very hard to hide a 100 solar mass star if it was close to us. It'd be very bright.
Yeah, but two stars.
But neutron stars don't make any visible light. They don't make many X-rays unless they're in a binary with a regular star, just like matter off of to make X-rays. And so you could hide a neutron star binary fairly close to the Earth, and until gravity wave detectors start to work, you wouldn't be able to find them very easily.
We're talking about split-second astronomy and things that apparently the USS Enterprise never encountered in space. With Dr. Lynn Kaminsky, we're going to finish up our conversation with Professor Kaminsky talking about gravity waves once we're back from this commercial break. Do stay with us. On this broadcast of Sci-Fi Overdrive, we've been exploring the universe and the endiverse, and as we come to the end of this broadcast, we were leaving the thought of gravity waves, and Professor Kaminsky was going to tell us what these things are.
Well, actually, most people call them gravitational waves, so I sort of slipped when I called them gravity waves before. But
so this isn't like artificial gravity?
Right. No, any mass or two massive objects that are orbiting around each other will put out gravitational waves. Also, things that explode a little asymmetrically can put out gravitational waves. And people are building detectors on Earth, for example, LIGO, which is the Laser Interferometric Gravitational Observatory, to look for gravitational waves. There's a LIGO in Washington, and there's another branch of it in Louisiana.
Ah, Joey Donovan's old hometown. Okay.
So that's one place where people are trying to look for gravitational waves. They are predictions from Einstein's theory of general relativity that have not ever been directly observed. There was an observation indirectly that they do exist, though, because there are several known systems that are comprised of binary neutron stars that can be observed as radio pulsars. And, in fact, a Nobel Prize was awarded to Joe Taylor and Russell Hulse for discovering the Taylor-Hulse pulsar binary and watching as this double neutron star binary orbit shrunk over a period of, I guess it's probably been at least 20 years now. And the way the orbit decayed, in other words, the two stars got closer and closer together, exactly tracked the curve that Einstein's theories would predict for the energy to be being lost in the system being given off as gravitational waves.
Okay, so that's one example.
Right, so we do have the examples of the binary pulsars giving out these waves.
How can we do more detection of gravitational waves?
Well, NASA is proposing a mission called LISA, which is Laser Interferometer Space Antenna, to go up and be made of 3 different satellites that will be out there at the L2 point, far from the Earth and Sun system. And these 3 satellites would act as a big interferometer to look for gravitational waves in space, where they would be able to be isolated from a truck going by or other types of things that make detecting gravitational waves on Earth be very difficult. The amount that space is compressed and expands when a gravitational wave passes through it, even a strong wave from something like a binary neutron star or a supernova, is just, maybe 1 part in 10 to the 25, really, really tiny amount.
Oh, so it's not like the folks in Louisiana notice that the universe is suddenly distorted.
No, and that's why you have to have more than one site to be able to check to see whether, the truck that went by in Louisiana and set off their detectors, did it affect one in Washington too.
And a little bit later on this year, the Gravity Probe B mission is going up.
Right, that's a satellite that's going to be testing a different part of Einstein's theory of general relativity, which is to see whether the Earth, because it's spinning around, is dragging space and time around with it. It's called frame dragging. That's one of the other major untested theories of predictions of the theory of general relativity, is that any rotating massive body should be able to drag its inertial frame around with it, drag its space and time around with it. And people have seen hints of that around big black holes by looking at X-ray data, but no one's been able to really verify it around something where we know how big it is and we know how fast it's spinning. And Gravity Probe B is going to be able to take the measurements to check that part of Einstein's work out for us.
Okay. In 1993, Dr. Lynn Kaminsky was named the California Professor of the Year by the Council of the Advancement and Support of Education. She's certainly done her bit to advance and support science education on this broadcast of Sci-Fi Overdrive. Thanks so much for joining us.
This is Sci-Fi Overdrive on Business Talk Radio. Be sure to visit our website, www.scifиoverdrive.com.